Hello, my name is Jacques, and today we're going to continue learning the basics of the Bevy Game Engine. Bevy is a simple data-driven game engine built in Rust. It's free and open source. This tutorial is the third episode in my Learn Bevy 0.10 video series. This episode builds on what we learned in the previous episodes. Today we're going to be continuing with our Bevy ball game project that we started in episode 2. In this episode, we'll move our player around using keyboard input, we'll keep the player inside the window, and we'll also start spawning in some enemies. Let's hop back into our code. Let's start by adding a movement system for our player. We're going to be using keyboard input. For our system parameters here, we're going to need a resource to our keyboard input. We're going to need a player query where we can change our transform component. And we're also going to need access to the time resource. For our query, this is going to be our first mutable query, where we need a mutable reference to the transform with the player component. And lastly, the time resource. In our function body, we're going to start by getting a reference to the player's transform. We're going to be using this if let OK block here. This is because our getSingleMut gives us the result type with either the mutable transform we're asking for or an error if it doesn't exist. Unlike the window that we saw before, our player entity isn't guaranteed to exist, so it's safer to use this if let OK block to get the mutable transform. Inside this block, we now have our transform and we can manipulate it. Next, inside our if let OK block, we're going to capture keyboard input, and based on the keyboard input, using the arrow keys or the WASD keys, we're going to determine the direction we want our player to move in, and then move our player in that direction by multiplying the speed and also the time since the last frame to get a smooth frame rate independent movement for our player. We're going to start with a direction vector of 0 since we don't know which direction we want to move in yet. Based on keyboard input, again, whether we're using the arrow keys or the WASD keys, we'll change this direction vector. Then we're going to check if the direction vector's length is greater than 0. That means there was keyboard input, and we want to normalize this input to make sure that our diagonals don't move faster than just going in a vertical or horizontal axis. Before we continue, we need to add a constant variable for our player speed. Here above our player movement system, we'll create a public variable, a public constant variable. We need to declare its type as well. And we'll set this to 500 for now. Back in our player movement system, after our direction has been normalized, this is our player's transform. On the translation component, we're going to add the direction vector we just calculated, multiplied by the player speed, and multiplied by time.delta time from our time resource. This allows the player to move at the same speed independent of any frame rate. Delta seconds is the time since the last update of the last frame, so you can think about it as the time since the last frame. That's the end of our player movement system. Let's register this in our main function, and here we're going to just add a regular system. This isn't a startup system. We want our player movement system to run once per frame. Let's cargo run our project now. Oh, I have a typo here. I need a vec3. Let's cargo run our project now. Here in our game window, we can now move our character around with the WASD keys or the arrow keys. There's one problem, however. We can go off the screen. Let's fix that with another system. Let's go to the bottom of our file here and create another system called Confine Player Movement, which we're going to use to keep the player within the window. For our system parameters here, we're going to need another immutable reference to the entity with a transform and player component, meaning our player entity, and our window query to get the window's width and height to bound our transform. Here in our query, I'm going to need another mutable reference to the transform because we're going to need to change it if we go out of bounds. And remember, we need our width filter as well here to get the player entity. And our window query. Don't forget to add a comma. In the body of our function, we're going to start out with the same if let OK block that we used in the previous system to get the player's transform. I'm going to call it player transform this time just to make it more clear. Note we use get single mut here as opposed to get single to get this reference to be mutable. The previous one here was also get single mut. We need to be very careful using the right methods to get either normal references or mutable references when we're working in Rust and Bevy. Just like before, let's get our window. See here we're just using the get single method because we just want a reference. Oh, and there you can see my IDE is showing me that result type that get single gives us. But here we're confident that we're going to get one, so we can unwrap it. Next, we're going to need another constant for our player size because we're going to reuse that quite often. I'm going to go to the top of the file, right below my main function here. Actually, let's put it at the top. And call it player size. It's also going to be an F32. And this is 64. This is the player sprite size. Oh, don't forget a semicolon. While we're here, let's move our other constant up here as well, just to keep things clean. Back down to our Confine player movement system. We're going to need some local variables here. Let's start with our half player size variable, which we're going to need in our calculations to bind the player inside the window. This is going to be 32. Let's calculate our minimum x, our maximum x, our minimum y, and our maximum y that our player can exist in. We add and subtract the player size here so that we keep the ball entirely inside the window, since the origin point of our sprite is in the center of the ball. Let's get the current translation of our player transform. We want this to be mutable because we're going to change it now in a second. Let's bound the player x position. If our translation's x is below the minimum, we want to set it back to the minimum. If it's above the maximum, we want to set it back to the maximum. Same thing with the y component. And now we just want to set that change translation to be the player's translation again. So we go player transform. Translation gets translation. Don't forget to register the system in our main function. We use add system here again because we want the system to run once per frame. Cargo run our application again now. And we see now, if we move our player to the edges, we stay inside the window. Right now, our game isn't much of a game, so let's add in a challenge. Let's spawn in some enemies. Here below our player component, let's add a new component called enemy. Let's add another system now to spawn in some enemies. But first, at the top of our file, I want to add another public const. Let's call this const number of enemies and let's set it to 4 for now. It's going to be of type uSize. Let's scroll down now below our spawn player function and our spawn camera function. Let's add another function here. We're going to call this one spawn enemies. Just like our spawn player function, our spawn enemies function will need 3 system parameters. Commands to spawn in the enemies, a query to the window to get information on the window width and height, and then the asset server to load in our PNG file for the texture. In the body of our function, let's start by getting the window. Here we're using get single again because we know there's only going to be one and we know it's going to exist, so we're allowed to unwrap it. Now let's create a for loop that runs over the number of enemies constant to spawn in that number of enemies. Inside our for loop, we want to spawn in enemies, but we want to spawn them in random positions within the window. To effectively generate random numbers, we're going to need to add another crate to our project. Open up your cargo.toml file and add the rand crate. Rand for random. Save, and in your terminal, run cargo build to make sure you're able to download it and compile your project. Okay, we now have the rand crate in our project. At the top of our main.rs file, we're gonna use the rand crate prelude to import it into our project. And with that, we can generate random numbers. Let's go back down to our spawn enemies function. Inside this for loop, we're gonna get a random x value and a random y value. Here, we get a random F32. This is going to return a value between 0 and 1. We can just multiply that by the window width to get a random x position within the window width. And Same thing here with our random Y value and the window height. We're now going to spawn in an enemy using our commands. So what do we want inside our spawn function? Again, we're going to need a tuple here, because we're going to need more than one component, so we need to wrap them in a tuple. Let's start with another sprite bundle, and similar to the player, we are going to care about the transform and the texture and leave everything else to default. We're going to set the transform X and Y component to be the random values we just calculated and leave Z at 0. We're going to set our texture to be the red ball to indicate that that's an enemy, and we're going to leave the rest of the components as default. Comma here after the sprite bundle, and now we also need to add in our enemy component that we just created. Let's register this spawn enemies function in our main function now. And our main function now looks like this. If we cargo run our project now, we see we've spawned in 4 enemies. This brings us to the end of episode 3. We've covered keyboard input to produce player movement. We've gone through more systems, more queries, and we've also spawned in our enemies. Still to come is enemy movement and adding danger, events, UI, and many more examples still to come as we continue to build out our first game. Thank you very much for watching. I hope this series has been helpful so far. Please post your comments and feedback below. I'd love to hear what you think. Let me know about the pacing, about the content, and again, thanks for watching and have a great day. See you in episode 4.